step into the 21st century. A revolution is underway. Today, in laboratories around the world, a new alchemy is at work. Everyday substances are being transformed into sophisticated materials that may change the way we live. Scientists and engineers are challenging the frontiers of what we know. They are improving and extending the lives of millions. With new tools and technologies, they are creating the materials of the future. They are making miracles by design. For Mario Andretti and his son Michael, speed is a family tradition. Together, they pursue one of man's oldest challenges: to conquer time and distance. Auto racing tests the strength and endurance of both man and machine. Built for the grueling Indianapolis 500, this car will go the distance faster than any automobile on Earth. At speeds upward of 200 miles an hour, racing has come a long way since its early beginnings. In 1911, Indy cars were made of wood and bound together with leather. Later, they were made of metal. Although sturdier, they were also deadly. As speed increased, so did the search for new materials that would improve safety as well as performance. Today, the Andretti's cars are faster and safer than ever, thanks to a new generation of advanced materials. Hoses made of Kevlar are fire-resistant. Axles of high-strength steel are twice as strong at high temperatures. Engines of aluminum and magnesium alloys are more fuel-efficient. Suspension links of carbon steel alloys and bodywork of graphite fiber composites are strong, yet remarkably lightweight. While windshields made of Lexan are shatterproof. Today, an Indy car is the proving ground for the cars we will drive tomorrow. Although this machine is state-of-the-art in engineering and design, the search for the winning edge continues. The newest member of the racing team is not a driver, nor is he a mechanic. Greg Olson is a 21st century alchemist. The Andretti's cars are built by Newman Haas. Olson has come here to make them a split second faster. Brian Lyles, chief designer, wants to reduce the weight of the car. The lighter it is, the faster it goes.
Crown and Pinion that we used this year. This one actually has done 550 miles, as you can see. It's beginning to polish up. As far as you know, there aren't any corrosion problems leaving.
Lyles hopes that Olson's work will help him improve the design.
Yeah, I'm sure you guys must have some new materials up your sleeves now that would actually enable us to probably redesign the whole thing and make it smaller and still function effectively. And for us, that will be the best solution, no doubt about it. Yeah, we'll take a look at it.
The challenge will require a new kind of steel. At Northwestern University in Evanston, Illinois, researchers are using an innovative concept that may help the Newman Haas racing team. Greg Olson and his group are developing new materials with specific properties based on the simple premise, need drives design.
Well, I think what's exciting about materials by design is that engineers no longer need to be limited by the materials that currently exist, but can start designing around the new materials that they would like to have.
Over the past 100 years, steel, a basic mixture of iron and carbon, has achieved an extraordinary level of sophistication. To improve it requires knowledge at the atomic level. A researcher uses an atom probe to unravel the components of a complex alloy. Each is made up of different atoms. An electric charge through the sample strips the atoms one at a time and counts them, revealing the alloy's chemical composition. By rearranging its atoms, Olson can alter the alloy's properties.
This particular prototype bearing steel that we're working on now is for an application in the Space Shuttle main engine turbopumps. And that bearing application involves a combination of stresses, very low temperatures, and a corrosive environment requiring properties well beyond those available in current bearing steels.
Bearing steel is one of the strongest alloys. Still, it breaks. A high-resolution electron microscope reveals why.
How's it going? It's pretty good. Is that the 100?
The atoms in the alloy are bound together in patterns much like grain in wood.
Yeah.
When this steel breaks, it comes apart at the boundary between grains.
Good. This is the simulation here?
Yeah, it's about 50 angstrom thickness, about 1.5 shots.
Olson suspects that here, the bonds between the atoms are weaker. To find out, the alloy's composition and structure are fed into a supercomputer. 400 hours of calculations will determine the amount of energy that holds the atoms together. Eventually, phosphorus is shown to be the weak link. Now, the design begins. Computers model a new alloy. To improve its properties and eliminate impurities, new compositions are tested. Vanadium and carbon increase strength. Lanthanum and oxygen will help eliminate phosphorus.
Yeah, if we keep vanadium at 0.25, we can keep the solution temperature under 1350.
Okay, that's good.
All right.
Let's see the final composition.
Final composition, here's where...
Olson's team developed a 7-ingredient recipe.
Okay, looks great.
Carpenter Technology in Reading, Pennsylvania will now turn theory into reality. "12 parts chromium will improve resistance to corrosion. Cobalt improves strength. A dash of nickel enhances toughness. After 3 hours, at 2200 degrees, a new alloy is created. The ancients forged steel by trial and error. Today, each step is precisely controlled, according to Olson's design. The new steel now undergoes a crucial test. The sample is subjected to 1,800 pounds of pressure before it splits. Greg Olson's new steel proves to be tougher than any bearing steel yet known.
Our results so far on experimental steels have demonstrated individual property improvements in fracture toughness and stress corrosion resistance that are quite substantial. And we are just now entering the phase where we've designed the first steels that bring together all of these properties in one alloy. We're just now characterizing the first prototype alloy, and the results at this point look very encouraging. It certainly does seem to hold the promise for a new class of steels with much improved properties over previous alloys.
Olson's new class of steels are destined for use in aircraft landing gears. For pilots, landing on an aircraft carrier is like hitting a brick wall at 140 miles an hour. If a steel can hold up here, it might just be tough enough for the Indianapolis 500. By probing the universe of the atom and manipulating the heart of matter, materials will be created that were once beyond the imagination. One thing is certain: the materials of tomorrow will find their way into every aspect of our lives. Each a miracle by design.